Hello everyone, welcome back to the channel Future Force. Today we're going to talk about one of the most hyped, most expensive, and ultimately most disappointing military technology projects in recent memory, the billion-dollar railgun experiment that promised to revolutionize naval warfare but instead ended up as an almost forgotten cautionary tale. For years, the railgun was showcased as the future of artillery, a weapon that could launch projectiles at speeds never seen before, using nothing but electromagnetic force. Defense officials, scientists, and military enthusiasts were captivated by the concept. The promise was clear: no explosive propellants, incredible range, hypersonic velocities, and reduced ammunition costs. But somewhere between the ambitious blueprints and real-world deployment, the dream started to crumble. On the outside, the railgun looked like a piece of technology pulled straight from a science fiction movie. Mounted on a test platform, it was a massive structure of metal, cables, and cooling systems. The barrel was long, sleek, and intimidating, a straight, high-strength rail assembly encased in protective housing to withstand enormous stresses. Every inch of the exterior was purpose-built for stability and durability. There were heavy reinforced mounts, advanced sensors attached along the barrel, and thick armor plating to protect the delicate electronics from environmental damage. The exterior wasn't about beauty, it was about raw function. Its imposing presence alone sent a message: this was supposed to be the weapon to end all naval artillery. When you looked at it, you could almost imagine it mounted on a destroyer, hurling projectiles hundreds of miles in seconds. The housing also incorporated multiple cooling vents, a robust cabling network, and high-voltage connection points that hinted at the immense power running through the system. For observers, the exterior was an engineering marvel, but as we'll see, what's on the outside is only part of the story. Inside, the railgun's design was where the magic, and the problems, truly lived. Two parallel conductive rails formed the core of the firing system. When a massive electrical current passed through them, it created an electromagnetic field strong enough to accelerate a projectile to several times the speed of sound. Between the rails was the armature, a conductive piece that held and propelled the projectile forward. Surrounding the rails were layers of insulation, advanced wiring, and magnetic field stabilizers to keep the enormous forces in check. The interior was a maze of high-tech components: power converters, capacitor banks the size of small cars, diagnostic systems, and cooling channels to prevent overheating. Each part was custom designed, with tolerances so precise that even a millimeter of error could throw off performance. But this complexity also made the system fragile. The wear on the rails was extreme, every shot eroded them, requiring frequent and costly replacement. And because the weapon relied on extreme bursts of power, the internal components faced stress levels no conventional gun had ever seen. Performance was where the railgun's hype reached its peak, and where reality started to push back. In controlled tests, the weapon could fire projectiles at velocities exceeding Mach 7, fast enough to travel over 100 miles in just minutes. This meant a destroyer equipped with a railgun could theoretically hit targets far beyond the reach of conventional naval guns, even rivaling some missile systems. The kinetic energy alone was devastating. The projectile didn't need explosives; its sheer speed could punch through armor, bunkers, or ships with catastrophic effect. In ideal conditions, the weapon could fire up to 10 rounds per minute, with each round costing a fraction of a missile. But here's where the numbers became misleading. Those ideal test conditions were carefully controlled: perfect power supply, stable platform, short bursts of firing. In real-world naval conditions, with constant motion, weather interference, and unpredictable targets, the weapon's performance dropped sharply. Power demands were immense, so immense that existing warships couldn't support the railgun without major redesigns or entirely new ship classes. And the barrel life, one of the biggest issues, turned out to be far shorter than expected, sometimes degrading after just a few dozen shots. Safety features were critical because the railgun wasn't just a giant cannon, it was a high-voltage, high-energy machine that could be dangerous even when idle. Extensive grounding systems ensured electrical surges didn't fry the ship's electronics or harm the crew. Emergency shutdown protocols were built into the firing controls, allowing operators to halt a shot sequence instantly if something went wrong. Cooling systems were monitored constantly to prevent catastrophic overheating. Shielding was placed around key electrical components to protect operators from electromagnetic exposure. And because the rails themselves could fail under stress, containment systems were designed to minimize debris if a rail fractured during firing. Despite these precautions, the weapon's inherent risks were significant. Handling massive bursts of electrical energy at sea is no small feat, and the margin for error was razor-thin. While there were no major accidents during testing, the potential hazards played into the Navy's caution when deciding whether to deploy the system. The unique selling points were what originally sold the railgun as the future. The promise of hypersonic speed, long-range precision, and minimal ammunition cost per shot was revolutionary. No need to store large amounts of explosive shells meant improved ship safety. Theoretically, a ship could carry hundreds of inert projectiles without worrying about a magazine explosion from enemy fire. The psychological advantage was also huge. Being able to hit a target from over 100 miles away within minutes could reshape naval tactics. Advocates pointed out that the cost per shot could be as low as $25,000 compared to multi-million-dollar missiles. And because the weapon was purely kinetic, it sidestepped many legal and political restrictions on certain types of explosives. But each of these selling points came with a footnote. The speed and range required flawless conditions. The cost advantage evaporated when factoring in the wear and tear on components and the enormous energy infrastructure required. And without a dedicated ship design, retrofitting existing vessels proved almost impossible. The price of the Railgun project wasn't just in dollars, though the financial side is staggering. Over the years, the U.S. Navy and defense contractors poured more than $1 billion into research, development, and testing. For that money, they got functional prototypes, plenty of data, and some stunning test footage, but no deployable weapon. The infrastructure upgrades alone would have cost billions more, including building ships capable of powering and cooling the system. In an era where budgets are constantly pulled between competing defense priorities, the Railgun's uncertain payoff became harder to justify. Meanwhile, advancements in missile technology continued to outpace the Railgun's practical gains. Hypersonic missiles began to offer similar speeds with greater flexibility and no need for a complete ship redesign. The cold reality was that the Railgun's price tag kept climbing while its role in the modern naval battlefield kept shrinking. In the end, the Railgun became a symbol of both ambition and overreach. It proved that the physics worked, that you could launch a projectile at hypersonic speeds using electromagnetic force. It also proved that translating lab success into battlefield practicality is an entirely different challenge. The exterior and interior design showcased cutting-edge engineering, the performance in tests was jaw-dropping, and the safety systems were impressive for such a radical weapon. But the unique selling points couldn't overcome the real-world limitations, and the cost outweighed the benefits. Today, the Railgun sits in storage, a reminder that not every billion-dollar military project ends in triumph. For some, it's a disappointment, for others, it's a necessary step in technological evolution, paving the way for future weapons that might finally deliver on the Railgun's promise. The story of the billion-dollar Railgun flop is a lesson in balancing innovation with practicality, a story of how even the most exciting breakthroughs can hit a wall when reality comes into play.